Hello there everyone, and thank you for joining me today for this lesson about function composition. We have two objectives for this lesson today. We are going to learn what composition is, we are going to evaluate function composition algebraically, and then also graphically as well. We're going to practice the mechanics of that, but first let's talk about a situation where composition might actually show up, out there in the real world. So suppose you're buying a car worth $16,000. Salesperson offers you a 10% discount and the manufacturer is giving a $2,000 rebate, all right? So you're going to pay less than $16,000 here when all is said and done. Let's find the final price of the car, supposing that the discount is applied first and then the $2,000 rebate, okay? So if we're going to apply a 10% discount to $16,000, which is what we're doing first here, we're going to take that $16,000, and one way to apply a 10% discount is just figure out what 90% of $16,000 would be. And we can do that quickly by multiplying by the decimal equivalent of 90%, which is 0.9. And when we do that multiplication, here's what we come up with. So when that 10% discount is applied, the cost of this car has now dropped to $14,400, all right? But then we have to take this $2,000 rebate into account, right? And the rebate is like, pay the money up front, but then you get it back after you submit the rebate, right? So we've got to take this $14,400 and ultimately we're getting $2,000 of that back, so we'll subtract $2,000 from that cost. So the final cost of this car, when all is said and done, is $12,400. We applied the discount first and then the rebate, resulting in this final cost here. Now that idea of applying two operations or two functions sequentially like that is kind of what we're all about with this idea of function composition. Now for what it's worth, if you're wondering if the order of that composition makes a difference, like let's say you were thinking, well, what if the rebate is applied first and then the 10% discount? Well, if it is done in that order, the final price is actually different. Not wildly different, but it is different. It's not equal. And that goes us to show that this idea of composition is not commutative. The order in which we apply these functions mattered because we got different answers if we change the order up. This was supposed to serve as a real-world example of this idea of function composition. So what exactly is this function composition? Well, mathematically, we take the results of one function and those results become the input to another function. Get one answer, plug it into another function, get another answer basically. And the image off to the right is a little bit silly, but it shows that. Take a number, plug it into G, you get an answer. Take that answer, plug it into another function, get potentially a different answer. There's two different ways that we can write function composition. We can write it using the composition symbol like you see here. It's like a multiplication dot, but it's open. More typically, you're going to see it written this way. I feel like this notation is more commonly used today using multiple grouping symbols, parentheses, if you will. The way that we read that is f of g of 4. Again, f of g of 4. And that notation right there would tell us to plug 4 into g, get that answer, then take that answer and plug it into f. So the way you tell which function to plug that input into first is the function that's closest to that input. Here, g is closest to 4, so 4 goes into g. Even in this notation, 4 is closest to g, so 4 goes into g first. I'm going to use probably this notation going forward for the most part. I feel like that's more commonly used, but be aware of the composition symbol, that open multiplication dot. So we'll start today by actually just calculating some composition, and then we'll look at a more graphical example here in a little bit. So here we have two functions, f of x and g of x, in the blue and red boxes in the top right corner. One of them is linear, the other is quadratic. We're going to practice our composition skills. So we're going to find f of g of 2, g of f of negative 4, g of 2, and then finally g of f of x. But let's start with f of g of 2. And if I try to color code this, it's going to get really obnoxious really fast. So I'm just going to stick to one color today. I'll stick to purple here. So we have to calculate first g of 2. We're going to plug 2 into that function g. Well, here is that function g. Its rule is x squared. So when we plug 2 into that function, we'll do 2 squared, which is 4. So g of 2 is 4, but that's not our final answer here. This composition now tells us to take that output and make it the input for the function f. So now we have to find f of 4, where that function f says take 3 times the input plus 8. And I'll try not to zoom out quite as much going forward so I can avoid giving you motion sickness maybe. But when you calculate this, you'll get a final answer here of 20. So f of g of 2 for these two functions f and g is equal to 20. Let's try another one where the order is reversed. Here's g of f of negative 4. We're going to find f of negative 4 first. And when we plug negative 4 into f, that's 3 times negative 4 plus 8. And when you crunch all that, you'll get negative 4. Now, negative 4 becomes the input for this next function in line g. So now we find g of negative 4. Well, that's negative 4 squared using our rule for g, which is positive 16. Be careful with your negative there. Negative 4, when you square it, when you multiply it times itself, will give you positive 16. Down here, we're composing a function with itself, which we can do. Let's find g of 2 first. G of 2 would be 2 squared, which is 4. And now we're going to take that and plug that number back into g. So that'll be 4 squared, which is 16. So you can compose a function with itself. We've done that here. This would be like applying a 10% discount repeatedly, basically, would be an example, I guess. Now over here, this is interesting. This is g of f of x. This is not a specific number we're plugging in, but rather we're going to calculate a formula for g of f using a generic variable here, x. Well, we got to plug x into f first, right? That's our rule. That's how we handle this. And if we plug x into f, we're going to get 3x plus 8. So f of x is 3x plus 8. But now that 3x plus 8 becomes the input for g. So this might be a little bit awkward. We haven't done this much up to this point perhaps, but we're not plugging a specific number into g, but rather an entire expression into g. We're plugging 3x plus 8 into g. So if I look at the function g up here, whatever I plug into g goes right there, and then we have to square it. So we're going to take 3x plus 8 and square it, which means to take 3x plus 8 multiplied by itself, which means we're going to have to FOIL this out. You can pause the video and practice your foiling skills here. I'm not going to go through every single step, but I am going to write down the final answer. So when we composed f of g of x, we got not a specific number for our final answer, but rather an algebraic expression, a formula, if you will, for calculating g of f of whatever. So for what it's worth, back here when we found g of f of negative 4, we could now just plug negative 4 into this, and we would get the same answer we got up here. So if we had to, compose in that order for a lot of numbers, we might do the legwork ahead of time and find our formula first so that we can just plug the numbers directly into that formula. This can be a little bit awkward, doing composition with variables instead of specific numbers. Just follow the rules, slow down a little bit, recognize that you're maybe plugging in an algebraic expression rather than a number, but you still stick to what the function tells you to do. So here's an example of evaluating function composition algebraically. Our second objective today is to do so graphically. I want us to get some practice reading graphs. Now the idea here is still the same. When we find f of g of 0, for example, we've got to figure out what g of 0 is first. What's different here though is that we don't have the actual rules for f and g, but we do have their graphs. So we need to use their graphs to find these values. Well, let's start with g of 0. G is the blue graph off to the right. G of 0 is the y value when x equals 0. And when x equals 0, g has a y value of 0 as well. So g of 0 is 0. Now that becomes the input for f. So now we find f of 0. So we look at the graph of f, which is the green linear equation over there. And when x is 0, y is 4. So f of 0 is 4. I'm going to switch colors to make these answers stand apart. G of f of 0. Let's pick up the pace a little bit. Let's start with f of 0. And sorry for all the zooming in and out. f of 0, when x is 0, we already know that f of x has a value of 4. 4 now becomes the input for the outside function g. So we look at the graph of g now, and when x equals 4, it looks like y is equal to 2. So g of 4 is equal to 2. Final answer right there. Let's do one more. G of f of 3. Let's find f of 3 first. When x equals 3, the green function f of x has a y value of 1. So f of 3 is 1. So 1 becomes the input for the outermost function g. So I go to the graph of g, and when x equals 1, y is also equal to 1. So our final answer here is 1. You're looking for the y values here. That's kind of the theme, but you have to do it in the right order, right? Do the innermost function first, get that answer. That answer becomes the input for the outermost function. Not a lot of work to show here at all. You might be able to do this just quickly mentally, and that's fine. I showed a little bit of work here, I guess, but a person maybe doesn't have to do so. So our lesson today was all about function composition. We talked about a real-world example of that and how the order actually does matter most of the time. There are some unique situations where it doesn't. But then we practiced function composition algebraically and graphically as well. Thank you for watching.